Hey there, algebra students. Welcome to one of our last reviews of the school year for Algebra 1 Plus. It's a bittersweet moment, but I have saved the best for last. We are going to be using this video to review the radicals and Pythagorean theorem skills we have learned in Chapter 10. This chapter covered everything involving radical expressions, radical equations, operations with radicals, and applying radicals to find missing side lengths of right triangles. So today that is what we are going to cover in this review video. Now this whole chapter, as you heard my kind of overview of all of those skills, there was one word they all had in common: radical. So we have to really understand what a radical is before we can apply it to the skills we've learned so far this year. So as a little recap, as a little review, a radical is another term for a square root sign, and it looks like that. The square root sign is basically the inverse of raising a number to a power of 2. So in this case, if I take the square root of 4, that's me asking what number could be multiplied by itself to equal 4. We're basically undoing the squaring that happened when we multiplied 2 times 2 to equal 4. So that's why the square root of 4 is 2. Now if I were to go and do the opposite of that, I would square 2 and I would end up back at 4. So that's why square roots and the power of 2, or raising a number to a power of 2, these are inverse operations. And that's going to be important for us to remember as we're applying it to our simplifying skills and our problem-solving skills. So with that being said, let's jump right into our first example. Here we're being asked to simplify products of 2 different radicals. So when we're simplifying, our goal here is to hunt for any perfect squares that are hiding within the radical. Because if I take the square root of 4, because 4 is a perfect square, the square root is going to be a nice whole number, 2. But let's say I took the square root of 3. Well, that's going to give me a very long, cumbersome decimal that's going to be very difficult for me to work with. So when we are simplifying radicals, we are going to be hunting for factors that are perfect squares. So we can take just those pieces, find those square roots, and then leave everything else that would have created those decimals we don't want to work with. We're going to leave all of those extra numbers inside the radical because they can't be squared easily, resulting in a whole number. So when we're doing this, because we're on the hunt for perfect squares, it's important to know what our perfect squares are. So first thing I do when I get, my test or my homework assignment handed out to me, I take my paper and I write my perfect squares on it, just so I have that reference list to look back and reference. So 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5, 25, 6 times 6, 36, 7 times 7, 49, 8 times 8, 64, 9 times 9, 81, etc. We could keep going, but we're going to pause there. Now, these are my perfect squares that I'm going to be on the hunt for, and I'm going to think about which of these could be factors in our larger numbers. So the first question they give us is the square root of 8 times the square root of 6. We could rewrite this, because it's multiplication, as 8 times 6 within the same radical. When we do that, we can then use our factor trees to hunt for those perfect square factors. So starting with 8, I'm going to ask myself, can any of these perfect squares go into 8? And as I go down my list, I see that yes, 4 is a perfect square, and it is also a factor of 8. Now I do the same for 6. I look at 6, There are no perfect squares that can go into the number 6. So I'm not going to be able to factor out any perfect squares. So instead, I am just going to break this down to 2 times 3, knowing that I'm going to be putting those pieces back together eventually, and I'm not going to be able to really pull any of these factors out of my radical, because neither 2 nor 3 are perfect squares. But going back to what we've already done, we did get a perfect square with our first factor. 4 breaks down to 2 times 2, and because those are duplicates, that's the perfect square that we're going to pull outside of the radical to make into our coefficient. So since 4 is a perfect square, we can find the square root of 4. The square root of 4 is 2. So that, now that we've taken the square root, it's no longer inside the square root sign. So now the 2 is a coefficient outside, but we still have this 2, and this 3 that we weren't able to find the square root of because they're not perfect squares. So those are still inside the radical. Now, when we do that, we see, oh, I have another pair, 2 times 2. So I can move those outside of the radical as well and multiply them by the 2 that is already there. So that becomes 4 on the outside, square root, all that's left on the inside is 3. So we've got 4 square root 3. Now there are a couple different roads you can take to get to the same answer. Perhaps you multiplied this to 48 and then broke it down. Or you broke it down first and then looked for perfect squares. As long as you're remembering the rules we've learned about our radicals, you should get to the same final answer. Now let's do the next one. This one now has coefficients on both radical expressions, or radical terms. So for this expression, we're going to multiply, and when we multiply radicals, we multiply the coefficients first, so that will become 4 times 3, and then we multiply the radicands, which are the numbers inside the radical second, so that will be 3 times 18. Now I could break these down as they are, the 3 and the 18, or I could multiply them and then break it down again. But either way, I know I'm going to have to multiply my coefficient first, so I'll do that. 4 times 3 is 12, square root. And I've decided, since 3 is already prime, I wouldn't be able to break it down any further anyways. I'm just going to leave that as a 3, and then break down 18, hoping to find a perfect square as a factor. So I'm going to go back to my list and see, okay, which of these factors could possibly go into 18? And the only one that works is 9. So that would be 9 times 2. Now we have our factors broken down, and I see that I have a perfect square. 9 is a perfect square, so we can pull the 3 outside and multiply it by the number that's already there. So this becomes 36 square root 3 times 2. We're going to combine the factors back together now that we've removed the perfect square. So 3 times 2 leaves us with 6. So the answer here was 36 square root 6. Next up, we're going to go down now and add some variables into the mix. So here we have the square root of 27tu squared. So just like we were doing before, we want to break it down into perfect square factors. So if I look at 27, the first perfect square that can go into that number is 9. So that would be 9 times 3. And then I'm going to break down the variables as well. So that's t times u squared. Now, 9 is a perfect square because it can be comprised of 3 times 3. U squared is also a perfect square because of u times u. So we can pull both of these out of the radical and move it into our coefficient spot. So this would become 3u square root, and then what's left over is just 3t. So that stays within the radical as our radicand and becomes our final answer, 3u square root 3t. Okay, let's do one last example of this. So to simplify this one, we have a larger number, but again, if I look at my list of perfect squares and work through the list, we can see that we can divide 108 by 9. That works. But we want to find the largest perfect square that 108 can be divided by. So if I keep checking, so we did 108 divided by 9, 108 divided by 16, doesn't work. 108 divided by, I know it won't be 25, so I'm going to jump to 36, and that's 3. So I can go through my perfect square factors and multiply them out, see if I get to my product, and if so, that's the factor I want to use. So 36 times 3, and then we have some larger exponents now. So this will be x to the 6th, y to the 4th, z squared. Now for this, I already know what to do with 36. That is a perfect square, so that's going to get pulled out of the radical. But I also have all of these exponents. So here's what we will do, because now these are exponents larger than 2. Here it was u squared, so it was just nice and easy to break it down and recognize that it was a perfect square. But when we have a larger exponent, we're going to divide that exponent by 2, because it takes 2 to make a square. So that answer that we get, that is going to be the new exponent outside of the radical. So x to the 6th, when we take the square root of that, we get x to the 3rd. So this will be 6 x to the 3rd. Y to the 4th, the square root of that is y squared. And z, 2 divided by 2 is 1, so the square root of z squared is just z to the 1st power. Now we're going to leave inside the radical everything else that's left. So that's the 3, and that's it. So our answer is 6x cubed y squared z times the square root of 3. All right, so that's section number 1, simplifying our radicals. Now let's move on to section 2, where we were now using operations and working with radicals within an operation or an expression. The major key that we learned for this section is that we need common radicands to be able to add or subtract our radicals. So let's look at the first one. The first one is the square root of 8 minus the square root of 2. Right now I can't do anything as they are because they don't have common radicands, with the radicand being the number inside. So we're going to have to kind of break these down and build them back up to make them have the same radicand. That way we can perform the operation. So 8 is the only number I can break down. It can break down to 4 times 2. And then we still have just the square root of 2 on the other side because I can't break that down. It's a prime number. Now 4 is a perfect square. So this will become 2 square root 2 minus the square root of 2. Now we have common radicands, 2 and 2, so we can subtract. But before I try to subtract, I want to remind myself that there is always a coefficient, even if we can't see it. So here we couldn't see the coefficient, but it's there and it's a 1. So when I do my subtraction, we'll subtract the coefficients. 2 minus 1 is 1, and then we keep the common radicand. So that's square root of 2. So 1 square root 2, our answer is the square root of 2. All right. Now the next one we're going to do is has coefficients this time. So here 5 is prime, so just like before, I can't break that term down, but I can break down the 75. And if I go through my list of perfect squares, I know 75 can be divided by 25, which is the perfect square. And that becomes 5 times 5. So 5 times 5 gets moved to the outside. So this will become 3 times 5 square root 3 plus 2 square root 5. Because all that was left in this radical was the 3, and this one we couldn't simplify any further. Now when I evaluate 3 times 5, and then I rewrite my problem, I see that at this point my hands are tied. I can't go any further than this because these are now prime. I can't break them down to try and find any common radicands. And I can't add these because these aren't common radicands. So if that happens, this is how you would leave it. It's simplified. We just weren't able to simplify it fully because we didn't have common radicands. All right. Now the next one, we have 4 terms, so we want to make sure to simplify and try and find which of those have common radicands. The first 2, I don't need to really rewrite or factor out because 6 and 2, I already know neither of those has a perfect square as a factor. But the square root of 50 does, and that can be the square root of 25 times 2. And 25 is 5 times 5. So that will be the factor that we can pull out of the radicand. So when we rewrite this, we can write 3 square root 6 plus 3 square root 2 minus 5 square root 2 plus, and then let's break down 24. 24, if I go through my list of perfect squares, the only one it can be divided by is 4. And 4 breaks down to 2 times 2. So that goes to the outside of the radicand, and then the 6 stays inside. Now I can see I have like terms here, and I have like terms here. So I will be able to simplify this a bit, even if not fully. So for my first like terms, we have 3 square root 6 plus 2 square root 6. So that's 5 square root 6. Then 3 square root 2 minus 5 square root 2. So that's negative 2 square root 2. I can't combine these any further. So this is my final simplified answer. All right, let's do one more quick example before we move on, because I know these were the ones that were a little tricky for us. So the square root of 50. 50 can be divided by 25 times 2. 18 can be divided by 9 times 2. 75 can be divided by 25 times 3. And 27 can be divided by 9 times 3. Now, I have some perfect squares here. 25, 9, 25, 9 again. So this becomes 5 square root 2 plus 3 square root 2 minus 5 square root 3 plus 3 square root 3. So I just took my square roots, moved them outside of the radical, the one thing I want to point out is that I made sure to remember that this was a subtraction sign. Otherwise, it could have thrown me off a bit. Now that I've done that, I'm going to look for like terms, and they're already grouped for me. So first, we have the radicand 2. So 5 plus 3 is 8, square root 2. And then our second radicand is 3. Now remember, this negative stays with the 5. So negative 5 plus 3 is negative 2, and then square root 3. So that would be our final answer. And I know I can't simplify it any further because these radicands are prime. All right. Let's go ahead and move on now to some multiplication with our radicals. So in our first example here, this is still from our operations section, we have a radical on the outside of a binomial. So this is where we are going to use those distribution skills that we've learned this year. So to distribute, we're going to take it one term at a time, and we would do the square root of 2 times 3 square root 7. Now, when we multiply radicals, we multiply the coefficients, and then we multiply the radicands. So this would be 1 times 3 is 3, and then 2 times 7 becomes the new radicand. Then we'll do it to the other term. So 1 times 2 is 2, square root 2 times 5 is 10. Now we can simplify. We get 3 square root 14 plus 2 square root 10. And this is where I would want to find a common radicand so I can add them together, but I've already come from having them broken down here, so I could see my factors, and I can see that all of these factors are prime and none of them repeat. So I can't break it down any further or find any new radicands that might have been invisible before. They aren't there. So this is as much as I can simplify it, so this is my final answer. All right, now let's do another example, this time double distribution. Here we have a binomial times a binomial. We are going to use our double distribution skills for this type of question. And so for double distribution, we're going to take the first term, 2 square root 5, and we're going to multiply that by the second set of parentheses. So the square root of 10 plus the square root of 6. Then we take our second term, minus 2 square root 3, and we're going to multiply that by the square root of 10 plus the square root of 6. All right, so now that we've set up our double distribution, now we have to do the distribution, believe it or not. So we distribute and multiply the coefficients first. 2 times 1 is 2, 5 times 10 is 50. Then 2 times 1 is 2, 5 times 6 is 30. Then we'll move on to the next set. Negative 2 times 1 is negative 2, 3 times 10 is 30, and negative 2 times 1 is negative 2, 3 times 6 is 18. Okay, so now we're looking to see if we have any common radicands. And to do that, I'm going to check what I have so far before I even try and break anything down. And in doing that, I notice we have positive 2 square root 30 minus 2 square root 30. Those two terms cancel out because they're the same but complete opposites. So that leaves us with 2 square root 50 minus 2 square root 18. I can't leave it like that because I know I can break this down. So 50, we can break that into 25 times 2, and 18 can be 9 times 2. So 9 gets moved outside the radicand, so does the 25, and we do that by taking the square root of each number. So the square root of 25 is 5. So this became 5 times 2 square root 2 minus 3 times 2 square root 2. Now I'm getting closer because I see I already have common radicands, so I'm moving in the right direction. 5 times 2 is 10 square root 2. 3 times 2 is 6 square root 2. 10 minus 6 is 4 square root 2. So that would be our final answer. Okay. We're moving right along. Now we're going to move on to some of our more recent skills, which asked us to solve equations involving radicals. So we learned when we solve equations, first we want to isolate the radical. Then raise both sides to a power. In this case, a power of 2. All right, so we are going to isolate the radical first, then raise both sides to a power. In this case, it'll be 2, and then we will solve. Those are the steps we will be following. So let's look at this first example. The square root of 5 minus 4x minus 6 equals 7. So I want to get the x alone by the very end. But to do that, I need to kind of break into this radical and get everything else out of the way. Before I can break into the radical that's kind of acting like a cage right now around these terms, I've got to move away everything out that's surrounding it that could get in the way of that. I kind of think of it as like I'm doing a jailbreak and I'm trying to break the x out of this little cell here. And to do that, I need to first move the guards, such as -6, away. So I'm going to use inverse operations to move all of my terms away from the radical. So that leaves me with the square root of 5 minus 4x equals 13. Now, the 4x and the 5 are both within the radical, and we can't get to either of them until we get rid of the radical. So this is where we want to use inverse operations. The same way up here, we had -6, so to get rid of it, we did the opposite and added 6. Here, we have the square root, so to get rid of that, we're going to do the opposite, and we are going to square both sides. Raising this square root to the power of 2 cancels it out, and that leaves us with just 5 minus 4x equals, and then we square the other side, and that gives us 169. From here, we have now just a simple equation that we can solve for our variable. So we subtract 5 from both sides. We get -4x equals 164. We'll divide by -4 on both sides. And our answer is x equals -41. Now to check my solution, I'm going to take that answer and plug it back in. So we have 5 minus -41 times 4, minus 6 equals 7. So I'm going to try and simplify this now. So 5 minus negative 41 times 4. All right, so 41 times 4 is 164. So this will become the square root of 5 plus 164 minus 6 equals 7. 5 plus 164 is the square root of 169 minus 6 equals 7. And the square root of 169 is 13 minus 6 equals 7. Now if I do 13 minus 6, I get 7, and that's equal to 7. So I know that I have done my job correctly. So let's move on to another one. For this example now, we have a term, I should say, on the same side as our variable and our radical. So step number 1, we're going to get the radical alone. And we're going to subtract 10 from both sides to do that. That's going to leave us with 2 square root x equals negative 10. Now I want x and my radical sign alone, and they're not. So the next step is to divide by 2. That leaves the square root of x equals negative 5. Now, at this point, we have to do some thinking. If I'm taking the square root of a number, then that means that I am finding what number times itself would equal that product. Well, the square root of a number can't be a negative, or at least we aren't sure. So in this case, because they're telling me the square root of x is negative 5, that is super suspicious. We can't have a negative answer to a square root. We can't do this. So this is when we get a no solution answer. Now, why doesn't this work? Well, let's say we squared that to get rid of the x. Negative 5 squared would be positive 25. If I plugged that in to my equation, 2 times the square root of 25 is 10, but positive 10. So I would end up with 10 plus 10, and that equals 20, not 0. So that's why this doesn't work with a negative. It would have to be positive for it to work, and it's not. So moving on, let's do another example. This time we have radicals on both sides. So to get to my variable, I have to first eliminate the radical by squaring both sides. That leaves h minus 5 equals 4 times 3. So when we're squaring a radical expression, the number that's not inside the radical can be squared. The number that is inside the radical just kind of breaks free. It just eliminates the sign and leaves the number as it was. So we end up with h minus 5 equals 12. If we add 5 to both sides, h equals 17. Now if I were to plug this in, the square root of h minus 5, well, let's see, the square root of 17 minus 5, that's the square root of 12, which breaks down into 4 times 3. 4 is the perfect square, and that equals 2 square root 3, which was the answer that we started with. So I passed the check. I know I did my job correctly. Okay, let's do one last one. This one has a little bit more substance to it, a few more steps. So first, remember the goal. We want to isolate the radical. Now, we do not want to divide by 5 first. Remember our third wheel rule. We want to get rid of any stragglers, any lonely guys. We can get rid of those first. So we do that by subtracting, and we get 5 square root a minus 3 equals 10. Now, our radical is closer to being alone, but it has a coefficient still. So next step, get rid of the coefficient. And to do that, we divide, because 5 square root a minus 3 is the same as 5 times the square root of a minus 3. So dividing by 5 gets rid of that and leaves just the square root of a minus 3 equals 2. Now this is where we have to get rid of the radical, and to do that we square both sides. So a minus 3 equals 4, and then we'll add 3 to both sides, and we get a equals 7. So to check our answer, I want you to check it on your own and see if we did our work correctly. Okay? All right, folks, you're doing great. We're almost done. We're going to cover one last topic, and that is Pythagorean theorem. Now, Pythagorean theorem, the meat and potatoes of that theory states that for a right triangle, a squared plus b squared plus c squared could be used to find the missing, or any missing side length. And now, this theorem is applicable only for right triangles. Within a right triangle, the sides that are touching the right angle will be the legs. That will be A and B. The side that is directly opposite the right angle, and also the longest, is C, the hypotenuse. Now we learned and want to remember that the hypotenuse across from the right angle has to be the longest side length. Now we can use this theorem, a squared plus b squared equals c squared. I got a little carried away there. Equals c squared. So we can use this theory to now find missing side lengths. So for the first one, a squared plus b squared equals c squared. They're telling us the leg is 6. So that's going to be a or b. I'll use a. So 6 squared plus b squared equals, and then they've told us the hypotenuse is 10. The hypotenuse always is by itself in the C position. So we will write equals 10 squared. Don't forget to square everything. Now once we do that, we evaluate, and we get 36 plus b squared equals 100. Then we're going to subtract 36 so that we can find what b is, the missing side length. So b squared equals 100 minus 36, which is 64. And at this point, I might be thinking I'm done, but b is not alone. Even though there's no number in front of it, there is still an exponent. So just like before when we were saying we would square something to get rid of the radical, if we have an exponent, we're going to use a radical to get rid of that perfect square. So that will cancel out and leave b alone. And then the square root of 64 is 8. So our missing side length is 8. And that makes sense. If I had gotten like 80, that would have been a red flag, because it wouldn't be a very possible triangle to have one leg 60, the hypotenuse 10, and then the other leg 80. Plus, the hypotenuse needs to be the longest side. So if they tell me the hypotenuse is 10, the answer I get for the other legs needs to be less than 10. All right, now let's try this next one. Here they gave us 2 legs, 30 and 15. So we'll use the same Pythagorean theorem, a squared plus b squared equals c squared. But now we're going to use 30 and 15 for a and b, and we're going to solve for c. So this will be 30 squared plus 15 squared equals c squared. So 30 squared, that's 900. 15 squared is 225, and that equals c squared. Watch those little exponents. They don't disappear until you've taken a square root. So if you had one up here and you haven't done a square root yet, or you haven't written a radical, you should still have that square down here too. All right, so now we combine 225 plus 900. We get 1125 equals c squared. And then just like before, the opposite, the inverse operation of raising to a power of 2 is taking a square root. So that square root of 1125, it doesn't give me a whole number. 33.5410, blah, blah, blah. So this is where we are going to want to simplify. So this will become the square root of, and just seeing that it ends in 25, I'm going to try and start with that. So 1125 divided by 25 is 45. And then 45 can be divided by 9. So that would be 9 times 5 equals c. Now 25 is a perfect square, so that can get pulled out as 5. And 9 is a perfect square, so that can become a 3. That means our answer, c equals 15 square root 5. Now because it's because it's Pythagorean theorem, I can write my answer like this, or we could follow the directions and round it to the nearest tenth. So if I have 15 square root 5, and then the square root of 1125, both of those gives me 33.5. So both of those would be considered my answer. All right, now the last thing here is a bonus skill using our Pythagorean theorem. Kalia wants to plant flowers in a triangular plot. She has 3 lengths of plastic guarding edging that measures 8 feet, 15 feet, and 17 feet. Determine whether these pieces form a right triangle. So if they form a right triangle, then our theorem, a squared plus b squared equals c squared, would be true. Now to test it, we're going to take the numbers they've given us, plug it into the equation to see if it works. The only thing we want to keep in mind is that a and b are interchangeable, but c always has to be the hypotenuse, so that means it always has to be the longest length. So that in this case would be 17. So we could rewrite this as 8 squared plus 15 squared equals 17 squared. Now 8 squared is 64. 15 squared is 225. And 17 squared is 289. Now to test if this would be a right triangle or just some other type of triangle, we add these two together. So 225 plus 64, and we get 289, and that is equal to 289. So that passes the check. So yes, it is a right triangle. If this had been like 245 equals 289, then we would say, nope, it's not a right triangle because it doesn't fit the theorem. But because it works out when we put our pieces into the right places, A, B, and C, we prove that a squared plus b squared does in fact equal c squared. All right, well, with that, we have covered all of the topic types that you will see on the test. However, I do think that it is important that you study further than just watching this video. So please use your study guide, your homework quick checks that you've been given back, your homework assignments, past videos, your textbook, and anything else you have to help you prepare, because this is one of our very final grades for this school year. So let's make it our best one yet. Good luck studying. I'll be available in the Math Center if you need me. Otherwise, I will see you for test day on Monday. Bye, guys.